Nuclear transmutation is the conversion of one chemical element or isotope into another. In other words, atoms of one element can be changed into atoms of another element by a process which occurs either through nuclear reactions or through radioactive decay. Transmutation technology has the potential to greatly reduce the long-term negative effects of radioactive wastes on human populations by reducing its radioactive half-life. Not all radioactive decay or nuclear reactions cause transmutation, but all transmutation is caused by either decay or nuclear reaction. The most common types of radioactive decay that do not cause transmutation are gamma decay and the related process internal conversion. However, most other types of decay do cause transmutation of the decaying radioisotope. Similarly, a few nuclear reactions do not cause transmutation, although in practice, most nuclear reactions and types of nuclear are the creation of all the chemical elements we observe naturally. Most of this happened in the distant past. However, one type of natural transmutation observable in the present occurs when certain radioactive elements present in nature spontaneously decay by a process that causes transmutation, such as alpha or beta decay. An example is the natural decay of potassium-40 to argon-40, which forms most of the argon in air. Also on Earth, natural transmutations from the different mechanism of natural nuclear reactions occur, due to cosmic ray bombardment of elements, and also occasionally from natural neutron bombardment. Artificial transmutation may occur in machinery that has enough energy to cause changes in the nuclear structure of the elements. Machines that can cause artificial transmutation include particle accelerators and tokamak reactors. Conventional fission power reactors also cause artificial transmutation, not from the power of the machine, but by exposing elements to neutrons produced by a fission from an artificially produced nuclear chain reaction. Artificial nuclear transmutation has been considered as a possible mechanism for reducing the volume and hazard of radioactive waste. History. The term transmutation dates back to alchemy. Alchemists pursued the philosopher's stone, capable of chrysoprase, the transformation of base metals into gold. While alchemists often understood chrysoprase as a metaphor for a mystical or religious process, some practitioners adopted a literal interpretation and tried to make gold through physical experiment. The impossibility of the metallic transmutation had been debated amongst alchemists, philosophers and scientists since the Middle Ages. Pseudo-alchemical transmutation was outlawed and publicly mocked beginning in the 14th century. Alchemists like Michael Mayer and Heinrich Heinrich wrote tracts exposing fraudulent claims of gold making. By the 1720s, there were no longer any respectable figures pursuing the physical transmutation of substances into gold. Antoine Lavoisier, in the 18th century, replaced the alchemical theory of elements with the modern theory of chemical elements, and John Dalton further developed the notion of atoms to explain various chemical processes. The disintegration of atoms is a distinct process involving much greater energies than could be achieved by alchemists. It was first consciously applied to modern physics by Frederick Soddy when he, along with Ernest Rutherford, discovered that radioactive thorium was converting itself into radium in 1901. At the moment of realization, Soddy later recalled, he shouted out, "Rutherford, this is transmutation." Rutherford snapped back, "For Christ's sake, Soddy, don't call it transmutation. They'll have our heads off as alchemists." Rutherford and Soddy were observing natural transmutation as a part of radioactive decay of the alpha decay type. However, in 1919, Rutherford was able to accomplish transmutation of nitrogen into oxygen, using alpha particles directed at nitrogen-14N plus alpha-17O plus P. This was the first observation of a nuclear reaction, that is, a reaction in which particles from one decay are used to transform another atomic nucleus. Eventually, in 1932, A fully artificial nuclear reaction and nuclear transmutation was achieved by Rutherford's colleagues John Cockcroft and Ernest Walton, who used artificially accelerated protons against lithium-7 to split the nucleus into two alpha particles. The feat was popularly known as splitting the atom, although it was not the modern nuclear fission reaction discovered in 1938 by Otto Hahn, Lise Meitner and their assistant Fritz Strassmann in heavy elements. Later in the 20th century, the transmutation of elements within stars was elaborated, accounting for the relative abundance of heavier elements in the universe, save for the first 5 elements, which were produced in the Big Bang and other cosmic ray processes. Stellar nuclear synthesis accounted for the abundance of all elements heavier than boron. In their 1957 paper Synthesis of the Elements in Stars, William Alfred Fowler, Margaret Burbage, Geoffrey Burbage, and Fred Hoyle explained how the abundances of essentially all but the lightest chemical elements could be explained by the process of nuclear synthesis in stars. It transpired that, under true nuclear transmutation, it is far easier to turn gold into lead than the reverse reaction, which was the one the alchemists had ardently pursued. Nuclear experiments have successfully transmuted lead into gold, but the expense far exceeds any gain. It would be easier to convert gold into lead via neutron capture and beta decay by leaving gold in a nuclear reactor for a long period of time. Glenn Seaborg produced several thousand atoms of gold from bismuth, but at a net loss. More information on gold synthesis, see Synthesis of precious metals. 197 O plus N 198 O 198 Hg plus N 199 Hg plus N 200 Hg plus N 201 Hg plus N 202 Hg plus N 203 Hg 203 teraliters plus N 204 teraliters 204 petabits transmutation in the universe. As noted above, the Big Bang is thought to be the origin of the hydrogen and helium in the universe. Hydrogen and helium together account for 98% of the mass of ordinary matter in the universe. The Big Bang also produced small amounts of lithium, beryllium and perhaps boron. More lithium, beryllium and boron were produced later, in a natural nuclear reaction, cosmic ray spallation. Stellar nuclear synthesis is responsible for all of the other elements occurring naturally in the universe as stable isotopes and primordial nuclide, from carbon to plutonium. These occurred after the Big Bang, during star formation. Some lighter elements from carbon to iron were formed in stars and released into space by asymptotic giant branch stars. These are a type of red giant that puffs off its outer atmosphere, containing some elements from carbon to nickel and iron. All elements with atomic weight greater than 64 atomic mass units are produced in supernova stars by means of nuclear reaction of lighter nuclei, called neutron capture, which subdivides into two processes, R process and S process. The Solar System is thought to have condensed approximately 4.6 billion years before the present, from a cloud of hydrogen and helium containing heavier elements in dust grains formed previously by a large number of such stars. These grains contained the heavier elements formed by transmutation earlier in the history of the universe. All of these natural processes of transmutation in stars are continuing today, in our own galaxy and in others. For example, the observed light curves of supernova stars such as SN 1987A show them blasting large amounts of radioactive nickel and cobalt into space. However, little of this material reaches Earth. Most natural transmutation on the Earth today is mediated by cosmic rays and by the radioactive decay of radioactive primordial nuclides left over from the initial formation of the Solar System, plus the radioactive decay of products of these nuclides. See decay chain. Artificial transmutation of nuclear waste. Overview: transmutation of transuranium elements such as the isotopes of plutonium, neptunium, americium, and curium has the potential to help solve the problems posed by the management of radioactive waste, by reducing the proportion of long-lived isotopes it contains. When irradiated with fast neutrons in a nuclear reactor, these isotopes can be made to undergo nuclear fission, destroying the original actinide isotope and producing a spectrum of radioactive and non-radioactive fission products. Ceramic targets containing actinides can be bombarded with neutrons to induce transmutation reactions to remove the most difficult long-lived species. These can consist of actinide-containing solid solutions such as N, O2, 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 or just actinide phases such as AMO2, NPO2, NPN. AMN mixed with some inert phases such as MgO, MgAl2O4, O2, tin and ZRN. The role of non-radioactive inert phases is mainly to provide stable mechanical behavior to the target under neutron irradiation. Reactor types: for instance, plutonium can be reprocessed into MOX fuels and transmuted in standard reactors. The heavier elements could be transmuted in fast reactors, but probably more effectively in a subcritical reactor, which is sometimes known as an energy amplifier and which was devised by Carlo Rubbia. Fusion neutron sources have also been proposed as well suited. Fuel types: there are several fuels that can incorporate plutonium in their initial composition at beginning of cycle and have a smaller amount of this element at the end of cycle. During the cycle, plutonium can be burnt in a power reactor, generating electricity. This process is not only interesting from a power generation standpoint, but also due to its capability of consuming the surplus weapons-grade plutonium from the weapons program and plutonium resulting of reprocessing. Spent nuclear fuel. Mixed oxide fuel is one of these. Its blend of oxides of plutonium and uranium constitutes an alternative to the low-enriched uranium fuel predominantly used in light water reactors. Since uranium is present in MOX, although plutonium will be burnt, second-generation plutonium will be produced through the radiative capture of U-238 and the two subsequent beta- decays. Fuels with plutonium and thorium are also an option. In these, the neutrons released in the fission of plutonium are captured by Th232. After this radiative capture, Th232 becomes Th233, which undergoes two beta- decays resulting in the production of the fissile isotope U-233. The radiative capture cross-section for Th232 is more than 3 times that of U-238, yielding a higher conversion to fissile fuel than that from U-238. Due to the absence of uranium in the fuel, there is no second-generation plutonium produced, and the amount of plutonium burnt will be higher than in MOX fuels. However, U-233, which is fissile, will be present in the SNF. Weapons-grade and reactor-grade plutonium can be used in plutonium-thorium fuels, with weapons-grade plutonium being the one that shows a bigger reduction in the amount of Pu-239. Reasoning behind transmutation: isotopes of plutonium and other actinides tend to be long-lived with half-lives of many thousands of years, whereas radioactive fission products tend to be shorter-lived. From a waste management viewpoint, transmutation of actinides eliminates a very long-term radioactive hazard and replaces it with a much shorter-term one. It is important to understand that the threat posed by a radioisotope is influenced by many factors, including the chemical and biological properties of the element. For instance, cesium has a relatively short biological half-life, while strontium and radium both have very long biological half-lives. As a result, strontium-90 and radium are much more able to cause harm than cesium-137 when a given activity is ingested. Many of the actinides are very radiotoxic because they have long biological half-lives and are alpha emitters. In transmutation, the intention is to convert the actinides into fission products. The fission products are very radioactive, but the majority of the activity will decay away within a short time. The most worrying short-lived fission products are those that accumulate in the body, such as iodine-131, which accumulates in the thyroid gland. But it is hoped that by good design of the nuclear fuel and transmutation plant that such fission products can be isolated from humans and their environment and allowed to decay. In the medium term, the fission products of highest concern are strontium-90 and cesium-137, both have a half-life of about 30 years. The cesium-137 is responsible for the majority of the external gamma dose experienced by workers in nuclear reprocessing plants and, in 2005, to workers at the Chernobyl site. When these medium-lived isotopes have decayed, the remaining isotopes will pose a much smaller threat. Long-lived fission products. Some radioactive fission products can be converted into shorter-lived radioisotopes by transmutation. Transmutation of all fission products with half-life greater than 1 year is studied in Grenoble, with varying results. Cesium-90 and CS-137, with half-lives of about 30 years, are the largest radiation emitters in used nuclear fuel on a scale of decades to a few hundreds of years, and are not easily transmuted because they have low neutron absorption cross-sections. Instead, they should simply be stored until they decay. Given that this length of storage is necessary, the fission products with shorter half-lives can also be stored until they decay. The next longer-lived fission product is Erdem-151, which has a half-life of 90 years, and is such a good neutron absorber that most of it is transmuted while the nuclear fuel is still being used. However, effectively transmuting the remaining Erdem-151 in nuclear waste would require separation from other isotopes of samarium. Given the smaller quantities and its low energy radioactivity, Erdem-151 is less dangerous than Cesium-90 and CS-137 and can also be left to decay. Finally, there are 7 long-lived fission products. They have much longer half-lives in the range 211,000 years to 16 million years. 2 of them, Tc-99 and I-129, are mobile enough in the environment to be potential dangers, are free or mostly free of mixture with stable isotopes of the same element, and have neutron cross-sections that are small but adequate to support transmutation. Also, Tc-99 can substitute for U-238 in supplying Doppler broadening for negative feedback for reactor stability. Most studies of proposed transmutation schemes have assumed 99 Tc-129I and transuranics as the targets for transmutation, with other fission products, activation products, and possibly reprocessed uranium remaining as waste. Of the remaining 5 long-lived fission products, She-79, SN-126 and PD-107 are produced only in small quantities, and the last 2 should be relatively inert. The other 2, Zr-93 and CS-135, are produced in larger quantities, but also not highly mobile in the environment. They are also mixed with larger quantities of other isotopes of the same element.